Hey guys, it's Mr. Lee. I just wanted to create a follow-up video because I wasn't really happy with how my lecture went, especially for period 5. I really ran out of time and I didn't really get to go through everything nearly as thoroughly as I would like to. So I just thought I'd make another quick follow-up video. Um, so when you're doing a normal calculation, okay, what that means is that you have some data in the real world where it's pretty close to the normal model. So you're going to use the normal model and you're going to calculate some calculations as if it actually is normal. Okay. So the thing that didn't make a lot of sense, especially in fifth period, because we kind of rushed through the lesson, was that, well, why do we have to standardize? If we have this great piece of technology that can do a calculation where you can just put in any normal model, like you can put in the mean and you can put in the standard deviation, why do we have to standardize? And the real answer to that is because the folks at College Board who write the AP stats exam, they want you to understand the actual process that the calculator is going through. And so to make sure you understand that process, they're not going to let you use the calculator on certain normal calculations. They're going to make you use what is called Table A. Okay, and Table A is one of the few tables you're going to use. There's a couple other tables, like the table of random digits, which actually is just an excerpt. But Table A is very common for you to use. So Table A, you can actually just Google it, stats Table A, but it's also right here in the very front of your book. So here's your textbook. If you just open up the front cover, there's Table A. And this is just the left half of Table A. So this is Table A for the negative z-scores. And then if you turn the page, here's Table A for the positive z-scores. Okay, so Table A is what we used to use, what I used in college before we had calculators that could do all of this stuff. Okay, so with Table A, you simply find your critical value, which is your z-score, and it's just going to show you a left tail. Okay, just a left tail. So what do I mean by a left tail? The density under, or the area under the curve, okay, that is just in the left tail portion of the density curve. Okay, so how Table A works is, let's say, and this is only on a standard normal distribution. So mu equals 0, sigma equals 1. So that's why out of the infinite number of normal models that there are, they are going to have you standardize the entire normal distribution first. So now you're doing all your calculations off of a standard normal curve. Okay, so let's say that your critical value, your z-score is, I don't know, negative 1.7. Okay, so what you're going to ask, what the question is going to ask you is something like this. Well, if it's going to look something like that. Find the probability that z is less than negative 1.7. Okay, what is that equal to? Okay, well, you have to be able to look that up in the table. So your z-score is negative 1.7. So you're going to do a whole state plan do conclude, okay, for just this one little problem. Okay, but let me just show you what the graph looks like. Okay, so here is my standard normal, 0, 1. There's 1, 2, 3, negative 1, negative 2, negative 3 sigma, right? So I'm going to go 0, 1, 2, 3, negative 1, negative 2, negative 3. Okay, and now let's shade the region of interest. So for this question, 1.7 is, oh, that's about halfway. That's a little bit more than halfway. And this is saying, well, if all of my z's are inside of the area under below the curve, right? If I randomly select one z, okay, one observation, one z-score, what is the probability that the z-score that I randomly select is below the critical value of negative 1.7? So my z here, my critical value is negative 1.7. That's just showing where this is. And then shade the region of interest. Is this a left tail or a right tail? Z is less than, so this is a left tail. So this question is asking, what is the area under the curve of this blue shaded region? Okay, So now I have no lower bound because remember that this curve goes infinitely without ever becoming zero, without ever touching the x-axis. Okay, so my lower bound is like negative infinity. My upper bound is right here, right? It's my critical value. Well, to use table A, these are all left tail calculations. So I just go to negative 1.7, and then up here, these numbers are for the hundredths value. So negative 1.7 is negative 1.70. So I would just go use the 0, 0 column. So negative 1.70, that answer would be approximately 0.0446. So how much area is in there? Well, not even 4.5% of the total area. Okay, 0.0446. Now let's say they do ask me for something with a hundredths value, like what's now this? Now my critical value is negative 1.73. So now I go to negative 1.7, but I have to go over to 0.03, and I have to line these up, and now my answer is 0.0418. Okay. And then my answer for my answer in context is that approximately 4.18% of the data, lies below the critical value of z equals negative 1.73. Okay. So that is how you use the table. Well, what about if you want a right tail? Okay. What about if I don't want a left tail? Well, what if I want a right tail? Well, because this thing is symmetric, if I wanted to know what the probability that z is greater than negative 1.73, that's just the opposite side, right? So if 4.18% of the data is left of negative 1.73, well, how would I figure out how much data is to the right of it? So that's equal to 1 minus the left tail. 1 minus that. It's just the complement of that, right? So that would be approximately equal to, 1 minus 0.0418, so 0.9582. So to conclude in context, from the standard normal model, approximately 95.82% of the data is greater than the critical value of z equals negative 1.73. Okay, so that is that. So that is how you use table A to find a left tail and also to find the right tail. Okay, just go to the critical value and either use the actual value from the table or the complement to that value. Okay, you can also find intervals. Okay, you can also find intervals, between two critical values. Okay, well, how would you do that? Well, that's a bit of a thinking problem for you, but if you look on my screen here, if you look on my screen, well, how would you, let me just share this, present this. Well, let's say, and sorry, this slide is kind of messed up, but let's say I have this, Tiger Woods hits his driver. It follows a normal distribution with the following parameters, 304, 8. Okay, what percent of Tiger's drives travel between 305 and 325? So now you have an interval. So you shade the region of interest, you draw the normal model that you're working with. Okay, and there's 305, there's 325, they shaded it in green. Well, how are you going to do this calculation using the table A? Okay, well, go to this first critical value over here of 325, and when you standardize this entire distribution, this 325 becomes a z-score of 2.63. Okay, so just go to table A and find, well, what is the left tail using a critical value of 2.63? So that's going to give you this entire area. Okay, and now, well, let's look at 305. what is the z-score for 305? When I standardize 305, that becomes a z-score of 0.13. Okay, and now go to table A and find, well, what is the percent of data to the left, or the left tail, when I have a critical value of z equals 0.13, and then I just subtract, right? To get this interval, I'm just calculating all of this, and I'm just subtracting away this white portion, right? So the overlap portion is what I subtract, and then I'm left with the actual interval. Okay, so that's how you'd find an interval using table A. Okay, and then finally, actually, let me end there, and I'm going to create a different video just doing a state plan do conclude. Okay, thanks, guys.